if you do this n times, okay, it will be pretty easy to show that x hat n will be equal to xn, which is the original signal, plus a bunch of quantization noise. This is bad, right? This is called accumulation. This is called quantization error accumulation, because the error between x hat and x turns out to be a summation of those q. Okay? And, well, you can always try to bank on the fact that they have zero mean. If you do a bunch of them, they cancel themselves out. But there's no warranty, right? Sometimes it can be really bad, right? So typically we would like to avoid situations like this. Okay? How do we avoid problems like this? We recognize that there is a mismatch between the encoder and the decoder. Okay? In the encoder, we do this. Okay? But in the decoder, we do this. Okay? So looks like there's a lot of difference. Okay? We have a difference here, and we also have a difference here. There are two differences. That's why there's an accumulation. Okay? So let's try to fix that. How about using the reconstructed sample for the difference? That way we reduce the mismatch. Okay? And I will propose this. Instead of using this, I propose using that. Okay? So instead of predicting x, okay, predicting from the original samples, I predict from the reconstructed sample. Okay? And that turns out to be a better scheme. So the modified scheme looks like this. Dn is equal to, which is the difference, is xn minus x hat of n minus 1. Meaning that this comes from the reconstruction. This comes from the reconstruction. And it's trivial for you to show that, so the decoder remains the same. Okay? We don't change the decoder, but we change the encoder. We change the encoder, and we'll be able to show that. So when you go home tonight, you can just take a little piece of paper with a pencil, okay, work out the details, and you're going to be able to show that x hat n is equal to xn plus qn only. So there's no more summation of the q. Okay, if we use this scheme. So this is called a closed loop, BPCM. This is the type of prediction that people in video coding use all the time. Okay, so the difficulty of this scheme is that you need the reconstruction. You need the reconstruction at the encoder. You need the reconstruction at the encoder. What does that mean? That means the encoder knows everything. The encoder has the decoder, right? That's how it decodes this x hat, and then use that reconstruction for future prediction. Okay, so that makes your encoder a lot more complex than before. Okay, because encoder has to be twice now, right? So it makes this scheme looks a lot more complicated. Okay, so this is the updated encoder. The encoder will have everything. It has the encoder, the original encoder, and it also has the decoder built in. Okay, so that we can reconstruction along the line. So you can show that by following the signal flow graph, you can show that the dn right here is xn minus x hat of n minus 1. This d stands for delay. Okay, that's anything passed through D will have an n minus 1 index. Okay, so because we're kind of running out of time, let me move through this a little. Yeah.
Here we also use task computation channel is perfect.
Yes, exactly. Exactly, right. If it's not perfect, there are a whole lot of things that's going to be good. Yes, right. This communication channel is an entirely different topic. Okay, right now, let's not worry about that. Let's assume that we're going to have a decent communication channel, and in practice, we do have decent communication channels, right? When I write you an email, it arrives exactly the same. Okay, it's not going to get any error. Okay, so we do know how to build very good communication channels. Okay, at a cost, of course. Yeah, that's another issue. So for now, let's just assume that we have a very good communication channel. We'll revisit this when we have time. Okay? From Zoe. So the generalization would. So this is how actually research is being done. Suppose that somebody proposed DPCM and you read it, and the first thing that you should always ask yourself is that, okay, can we make it better? Can we generalize that to something a little bit more intelligent and get better performance? So generalization of the scheme. Okay. So one thing that we can do is to replace a simple delay operator. So instead of predicting x n from just x hat of n minus 1, okay? Maybe we will predict from more than just one guy or a linear combination of the past samples, right? So we will be able to use something we call a predictor or just a filter operation, just any filtering operations, right? And hopefully we're going to do better than a simple delay, right? The delay in Entung's course is just a very is a trivial filter, right? Delta of n is a very boring filter. It doesn't really give you much, a very good performance. So usually you do a lot better so we will do this upgrade, right? We upgrade this delay operator by some kind of prediction operator, okay? So this P typically is an FIR filter, okay? And as you can see, if I put P here and P here, everything works exactly the same way, okay? It's still a closed loop design, okay? It behaves exactly the same way, but it just may be offering you a better prediction, so that dn will be smaller. Okay? The entire goal is to make the prediction small, okay? So that we can compress it better. So xn, pn, you can think of pn as an operation that give you predict x hat of n based on the observation, based on these observations. These are the past observations. Okay, you already see them. You know some kind of behavior, and you use the past samples to predict the current one. Okay, so you can write it as a linear combinations, and this is going to be what you're using to predict xn. Okay? So now, next question. How do we find out this AI, right? Which is the weighting cost. That's the main thing. Basically, how do we design the filters here? So that what? So that the PS is the mean square error between x and x hat is minimized, for example. Okay, that is a very common thing to do. Okay? So let's try to pose this problem. This is called the optimal linear prediction problem. Okay, and I don't know if anyone covers that, but it's a kind of we're going to show that this is just a winner. Okay, we can if we observe the autocorrelation, the correlation between the samples, we'll be able to design these filters in a few mathematical steps. Okay, so I'm going to pose this problem. Find the set of AI such that the distortion or the variance of the noise, okay, between xn, which is the current samples, and the prediction is minimum. Okay? Now, if this is minimum, dn will turn out to be very small. Will be the smallest that you can ever produce. And that small guy, when you go into Q, will generate a lot of zero. And those zero coming into the entropy coder will give you a minimum amount of bits that you can send over the communication. Okay? So that's the key. Okay? So how do we do this? What's our dear friend? Our dear friend is the differentiation operators, right? Let's take derivative, set it equal to 0, right? That's what we do essentially, most of the time. Okay? So how do we take derivative of this guy? Yeah, just do partial derivative with respect to AI, right? Okay? But before we do that, I think I need a couple of assumptions. Okay? The assumption is that my signal will be Y-stand stationary because I don't know how to deal with multi-dimensional signal very well. Okay? Too bad. this Y-sense stationary is pretty much the only random process that allows us to do simple mathematical derivations. Okay? I'm going to assume we have high bit rate, so fine quantization, so that I have that uniform distribution in the noise. Okay? It's also another very typical thing to do. And let me remind you that Y-sense stationary means that the expectation of xn with xn plus k is only dependent on k. How far you are away. That's it. Okay? Which is pretty reasonable in a lot of natural images. The farther you are away, the less correlation you have. Okay? So, and Pn, so Pn typically look like this, okay? Pn in closed loop is has the head, okay? But I'm going to make this assumption as well, okay? That with high bit rate, okay, having head or not having head is roughly the same, okay? Because you have very small quantization step size, so you make very little error, okay? So I'm going to make this approximation, okay? So this is actually the optimal linear prediction in terms, this is an open loop design, right? Open loop. Closed loop means you have the head. Open loop means you don't have the head, okay? So this is open loop, and the approach is taking the derivatives that are equal to 0 and all that, okay? So let's think about this. How do I do this? I take derivative of d with respect to ai, and the only terms that, so I have to do this for a0 and a1 and a2 and a3 and a4, okay? When I do a0, I pick up only one guy, right? The first term, sorry. I do a1, a2, a3, the way I write my summation, okay? So first I'm going to do a1. First I'm going to do a1, right? When I do a1, okay, remember I have the square here. I switch the orders of expectations, which is an integral with derivative, okay? And take the derivative of the guys inside. I have this 2 here. I have the negative sign because I have a negative sign here. And then the chain rule give me x of n minus 1. Okay? I only pick up the first guy, right? So if I do it with a2,